To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today I am going to continue with the extra questions related to electromagnetism. So in the previous two chapters also we have been discussing questions. You all are familiar with the theory, so I'll move on to the questions. Extra question 2. So here of course you need to write the answers. So I'm sure you will answer the questions first by yourself and then you will compare your answers with my discussion. So then the first question. What is magnetic field? Now you all know there are magnets, both permanent magnet and electromagnets. And when there is any type of magnet, around the magnet there is a region where it has an effect. That is, let's say you have a bar magnet. Now if we consider, let's say we have a bar magnet like that. And around this magnet, now say if you have a pin here, that pin will not get attracted to the magnet. But when you bring the pin a little bit more closer, then of course you will see that the pin, it is a paper clip or a safety pin that will get attracted to the magnet. So this area around the magnet where there is an effect of the magnet is what we call as the magnetic field. And you all know normally for a bar magnet, the magnetic field, let's say if this is north and south, starts from north and goes towards the south. We have observed that. And on the other side also. So there is a region where you have the magnetic field lines. So that is what you need to write here. What is magnetic field? A region around the magnet in which the magnet has an effect is known as magnetic field. Magnetic field. So it has to be around the magnet where the magnet has its effect. And that region is known as magnetic field. Then, the second part of the question, write the two types of magnets. So I mentioned this to you all, the permanent magnets and the electromagnets. So permanent magnet, electromagnet. So you all are familiar with permanent magnet, students. The bar magnet, ring magnet, magnetic poles used in the say direct current motor, all those are permanent magnets. Even in the dynamo what we use are permanent magnets. But electromagnets, when electricity is supplied, the particular, actually it is the iron or steel that gets magnetized. Say for example, when we need to transport scrap iron from one place to the other, for that a disc is used that becomes a magnet, an electromagnet whenever necessary. So that is electromagnet. Then the third part of the question, write 3 devices that use magnets. Now you are familiar with devices that use magnets. The devices that we discussed in our lesson. You can remember the loudspeaker. Then we have the direct current motor, the alternating current dynamo, the bicycle dynamo, even the microphone, moving coil magnetic microphone. All of them use magnets. You all are familiar with that. In addition to that, you are even familiar with these pencil cases that have magnets on them. Fridge magnets, we use fridge magnets to hold on to notes or something. So for that we use the fridge magnets. Like that, there are other devices also that use magnets, but I will write examples that we have discussed in this lesson. So here I will say direct current motor, or you can write it as DC motor, then dynamo, and let's say moving coil microphone, moving coil magnetic microphone. You can even write the loudspeaker also. In addition to that, we have even discussed that the voltmeter, ammeter, which are analog voltmeter and ammeter, and even the galvanometer, they all function based on the same principle. So there is magnet. So similar to direct current motor and loudspeakers, we have the analog voltmeters, ammeters, as well as the galvanometers. So they all use the same principle, whereas dynamo and moving coil magnetic microphone, they use electromagnetic induction. So all of them use magnets. So you can write any three devices. So these are the first three parts of the second question. So with that, students, I'll move on to the next question. Extra question 3. An activity carried out to observe a magnetic effect due to a straight conductor carrying a current is shown in the diagram. So if you look at the diagram here, you can see there is this circuit where you have the batteries there. So here batteries. So you can see this is the positive terminal, negative terminal. So in this circuit, if the switch is closed, current will flow in this direction. So here it will be from A to B. Current flow will be from A to B. That is when switch S is closed. Then you can see this blue color line AB is the conductor, and under the conductor, below the conductor, there is a compass. You all know the function of a compass. The pointer, the indicator of the compass, will point towards the north-south direction, like shown here. You can see north and south. So it points that way. So you are familiar with this activity, students. What happens here? When we close the switch, you will see a deflection in the compass. Why is that? Now the compass, the pointer deflects when there is a magnetic field around it. Now when the switch is open, the compass does not deflect. That means there is no magnetic field. But once you close the switch, there is a magnetic field generated due to the current flowing through this conductor AB. So because of that magnetic field, the compass shows a deflection. So that is the magnetic effect of current. And this was actually initially introduced to the world by Hans Christian Ørsted. You all can remember the scientist. So he was the one who introduced this to the world. So that is the observation of this activity. And also you all know, if we change the terminals of the battery, then also when we close the switch, there will be a deflection, but the deflection will be in the opposite direction. You all can remember that. And below the conductor and above the conductor also, you will see deflection. Now here, as it is, when the current is flowing this way, below there will be deflection in one direction. But when you bring the compass up, the deflection will be in the opposite direction. Now you all know the reason. We use the right hand grip rule or the Maxwell corkscrew rule. So you know, when let's say if current flows from A to B, the thumb has to point towards the direction AB and the rest of the fingers show you the direction of the magnetic field. That is the right hand grip rule. So above, the magnetic field will be in one direction. Below, the magnetic field is going to be in the opposite direction. So that also can be observed using the compass. I'm sure you all can remember the activity. So then if we answer the questions, so the introduction is an activity carried out to observe a magnetic effect due to a straight conductor carrying a current is shown in the diagram. The first part, write the name of the scientist who first observed that a magnetic field is generated around the vicinity of a conductor when electric current flows through it. So that is, I told you all, Hans Christian Oster. So you have to write that name. Hans Christian Oster. So Hans Christian Oster is the scientist who observed this initially. Then the second one. What will be the observation when switch S is closed? So what will you observe? You will observe a deflection in the pointer of the compass. Pointer of compass. Pointer of the compass will deflect. So here, since it is the observation of the activity, we don't really need to specify the direction unless they ask you for that. So here, if you write pointer of the compass will deflect, or you can say there will be deflection in the pointer of the compass, that's more than enough. Then the third one. What can you conclude from the above observation? What can you conclude? That there is a magnetic field generated due to the current flowing through the conductor AB. A magnetic field is generated around conductor AB when current is flowing through it. Or you can say when there is a current flow. So a magnetic field is generated around the conductor AB when current is flowing through it. So that is the conclusion. Is that clear, students? So these are the answers. With that, I will move on to the next slide. Here I have extra question 4. A magnetic field is generated due to a current flowing through a conductor shown in the diagram. So here also a similar one. You can see the diagram. Here of course they have said battery. They have shown the conductor AB, the connecting wires. That's it. But they say a magnetic field is generated due to a current flowing through a conductor shown in the diagram. So you all can understand that. First one, predict the direction of the magnetic field when current flows from A to B in the conductor. So if it is A to B, that is going to be downwards. So how do you find it? Now if this is the conductor AB, the current is going to flow from A to B. Then what is the rule that we use? Either the right hand grip rule or the Maxwell corkscrew rule. So if I use the right hand grip rule, you can use any method. If I use the right hand grip rule, now if I hold my thumb pointing towards the direction of the current flow, A, B, then the rest of the fingers point towards the direction of the magnetic field. So this way it is going to be the clockwise magnetic field. It will be clockwise around the conductor. So predict the direction of the magnetic field when current flows from A to B. So it is going to be like that. A to B. Now if it's the magnetic field, that is going to be in this direction. So in the clockwise direction around conductor A, B. That is how you will get the magnetic field. Then, predict the direction of the magnetic field when current flows from B to A in the conductor. So, here if the current flows from B to A, again if I have the conductor like this, I will use the right hand grip rule. So, my thumb will point towards the direction of the current flow B to A, and the rest of the fingers point towards the direction of the magnetic field. So, it's going to be this way. So, that is going to be anti-clockwise direction. If I show that here, A, B. Now, that is going to be anti-clockwise. The direction of the current flow in this A to B, here it is B to A. So, then of course, predict the direction, it is in the anti-clockwise direction around the conductor AB. So, here conductor is AB, but the direction of current flow initially it's from A to B. Here it is A to B, here it is B to A. So, when the direction changes, you can see the direction of the magnetic field also changes. Is that clear, students? If you use the Maxwell corkscrew rule, how do you find out? The direction of the movement of the corkscrew points to the direction of the magnetic field. So, if the current is flowing from A to B, you have to rotate the corkscrew this way. So, the corkscrew will be moving down. At the same time, it would be a clockwise rotation. If it is coming up, anti-clockwise rotation, it's going to move up. So, B to A, it is going to be anti-clockwise. So, that is how we find the direction of the magnetic field. Is that okay, students? So, you can use either method, either the right hand grip rule or the Maxwell corkscrew rule. Then, the third part, what can you conclude from the above observations? What can you conclude? Already we said that there is magnetic field around the conductor when current flows through it. That is given in the introduction also. But in this, from these two observations, you can understand that the direction of the magnetic field depends on the direction of the current flowing through the conductor. So, that is what we need to write here. Direction of the induced magnetic field around the current carrying conductor depends on the direction of current flowing through the conductor. Through the conductor. So, that is what we can conclude from this activity. Direction of the induced magnetic field. Here I have said induced magnetic field because you all know it is the electromagnetic field. It's an electromagnet, so that is the induced magnetic field. Due to the current, there is a magnetic field acting around it. So, direction of the induced magnetic field around the current carrying conductor depends on the direction of the current flowing through the conductor. Or you can stop it right here also, direction of the current. Is that okay, students? So, this is the activity that we have learned before also. So, with that, I'll move on to the next slide. Here I have extra question 5. A magnetic field is generated due to a current flowing through a conductor. So, all related to the previous activity, the same observation. Induced magnetic field or magnetic effect of current. The first one, write the names of the laws that can be used to predict the direction of the magnetic field in the activity. So, you all know there are 2 laws. I have mentioned this, right hand grip rule or the Maxwell's corkscrew rule. So, that is what we need to write here. Right hand grip rule and Maxwell's corkscrew rule. So, there are 2 rules that we can use, right hand grip rule and Maxwell corkscrew rule. Then, mark the direction of the magnetic field in the following instances. So, here you can see this is a conductor. They have shown the direction of the current flow. So, if this is the conductor. And the red color arrows point to the direction of current. So, here it is current. And here also the current I. Now, how do we find the direction of the magnetic field? Using the right hand grip rule or the Maxwell corkscrew rule. So, here of course, if it is Maxwell corkscrew rule, if you rotate it like this, the tip of the corkscrew will move towards that direction. At the same time, the rotation will be like this around. So, if you look at this as the board or the paper, then what happens? There will be magnetic field lines coming out from above and going into the board from below. So, it will be in this direction. So, there how do we mark it? You can remember a circle with a dot inside represents that the field lines are coming out of the board. Circle with a cross inside represents the magnetic field going into the board. So, here on top it is going to be a circle and a dot inside. At the bottom it is going to be crossed like that. So, the magnetic field, if we check it with the right hand grip rule also, you can see that way thumb and my fingers are going into the board below and coming out from above. So, this is coming out and going in. The same way, if we look at the second instance, what is the difference? The current is flowing in this direction. So, right hand grip rule has to be this way. So, the magnetic field goes in from the above the conductor, comes out below the conductor. So, the symbols have to be circle and cross above, circle and dot below. So, that is how we indicate the magnetic field. Is that clear, students? So, we have the conductor, we have the current flowing through it, and we have denoted the magnetic field. So, this is the magnetic field. Given by these symbols below and above. Is that clear? So, that is again related to magnetic effect of current. So, with that, students, I'll move on to the next slide. Extra question 6. So, here also you can see it is an activity based question. We'll read the introduction first. An activity carried out in order to find out whether a force acts on a current carrying conductor placed in a magnetic field is illustrated in the figure. So, they are trying to figure out or find out whether a force acts on a current carrying conductor placed in a magnetic field. BC is an aluminium conductor. So BC is an aluminium conductor. Now if we look at the diagram, you all can see here students, this is a U magnet. Now here you can see north and south poles of the magnet. So you know the magnetic field will be acting downwards, north to south. Then across that you can see the aluminium conductor BC placed within the magnetic field. That also you can see. Then here you can see there are two brass rods kept on the magnet on this side. These two ends are kept on the magnet, and on this side they are fixed into this thick cardboard piece. So this thick cardboard piece is used to hold those two brass rods in place. And on top of that only we have the aluminium conductor BC. You all can see that. So you can understand and you can remember doing the activity. The BC conductor can move freely. It's not fixed. So it can move freely. Then on this side you can see points A and D. A is connected with batteries. The positive terminal is here. The negative terminal is there. So then it is continuously connected to switch S, that is connected to D. So when the switch is closed, there will be a continuous circuit, a complete circuit, and current can flow through it. And according to this setup, the current will flow from A to B, then B to C and C to D. Current flow. That is when switch is closed. When you close the switch, current will flow in the direction A, B, C, D. And the magnetic field is from north to south, top to bottom. So this is to observe whether a force acts on a current carrying conductor placed in a magnetic field. So magnetic field is there. When switch is closed, current will flow. So the conductor is BC. It is an aluminium conductor. So you all know students, when there is no force acting on the conductor, there will be no movement. But when there is an unbalanced force, there will be a movement. You can see the rod moving. That is if there is a force acting on it. So that's what we do. We close the switch and observe. Then you will see the BC rod moving either towards the magnet or away from the magnet. And you all know that depends on different factors. The direction of the current flow and the direction of the magnetic field. Right. So now if we look at the questions. The first part, write the observation when switch S is closed. You can see the rod moving. That is what you will see, but from experience you all know when the current flows this way. Through the conductor BC, it is going to flow from B to C direction. So there, of course, the rod will move outwards, out of the magnet or away from the magnet. So you can say BC rod moves. If you write that itself, it is okay. Otherwise, you can say out of the magnet. So here you are sure that the rod will move, but using the Fleming's left hand rule, you can predict that the rod will move out of the magnet. How do we do that? You can see when positive terminal is here, so current flows this way, B to C. We use the Fleming's left hand rule. So magnetic field is downwards, index finger down, and the middle finger has to be this way, B to C. The thumb points outwards. So the rod will move out of the magnet or away from the magnet. BC rod moves out of the magnet or away from the magnet. The second one. What rule can you use to predict the direction of the movement of the aluminium conductor? So like I said, Fleming's left hand rule. Fleming's left hand rule. Fleming's left hand rule. So then I'll move on to the rest of the questions. Here we have part 3. Predict the direction of the movement of the aluminium conductor using the above rule. So we have already done that, but just to confirm, now you all know the current flows in this direction when the switch is closed. So BC rod, the current flows this way. BC current is flowing from B to C. And the magnetic field is down. So again, if you apply the Fleming's left hand rule, you will see the current flows this way, magnetic field down. This is the magnetic field, this is the current flow. So the movement, the force is going to be out of the magnet. So that is if you predict the direction out of the magnet. Or you can say away from the magnet, or away from the magnet. So like I told you all before, students, in the first question, if you just say the BC rod will move, that is more than enough, because here they have asked for the direction. Then, what will be the observation if you repeat the above step after changing the terminals of the battery? So, if you change the terminals of the battery, what will happen there? Now, when you change the terminals of the battery, so then this will be positive, negative, positive, negative, positive. Then, of course, if you change, then the current is going to flow from here. Current flows in this direction. So, in the BC rod, then current will flow this way. CB direction. Current is going to flow in the CB direction. So, this finger has to be towards the CB direction, but still the magnetic field is downwards. So, magnetic field down, current flow is going to be in the CB direction. So, the thumb points into the magnet. When you hold the three fingers perpendicular, thumb will point into the magnet or towards the magnet. Then, the BC rod will move into the magnet or towards the magnet. So, here, what will be the observation if you repeat the above step after changing the terminals of the battery? BC conductor will move towards the magnet. So, from this, what can you all understand? You can remember when we change the direction of the current flow, keeping the direction of the magnetic field the same. Direction of magnetic field did not change, only the direction of current flow changed. So, then the direction of force will change. You all can remember that. So, that is the observation. Then I'll move on to the next part. Here we have part 5. What will be the observation if you repeat the activity after changing the poles of the U magnet? So, the magnetic field is upwards. So, this is also related to the first activity. The same way, this is how it was initially. Now, what we are going to do is, we are going to change the magnetic field. South to north. Earlier it is north and south. Now if we change it, it is going to be south to north. So the magnetic field is going to be this way, north to south. But still the current will flow from BC direction. Why? The positive terminal is here, negative terminal is there. So current flow is going to be in the direction BC. Current flows in the direction BC, but the magnetic field is acting upwards. So again, if we hold the three fingers perpendicular to each other, the index finger magnetic field upwards. But the current flow is going to be in the BC direction. Then the thumb points towards the magnet. So the BC rod will move into the magnet or towards the magnet. So what will be the observation if you repeat the activity after changing the poles of the U magnet? Then what will happen? We can say conductor BC will move towards the magnet. You can remember this, students. We did it during the activity also. So here direction of current flow does not change, but the direction of the magnetic field changes. So then direction of the force changes. Conductor BC will move towards the magnet. So what can you conclude from the above observation? That is what I mentioned now. The direction of the force acting on a current carrying conductor placed in a magnetic field depends on the direction of the magnetic field. So here you can see the direction of the force acting on a current carrying conductor placed in a magnetic field depends on the direction of the magnetic field. So you have to give this as well. You have to say the conductor is placed in the magnetic field and current is flowing through it. So current carrying conductor. Then only there will be a force acting on it. And the direction of the force will depend on the direction of the magnetic field. Is that clear, students? So then we'll move on to the next part. So here it is part 7. How can you increase the speed of the movement of the conductor BC? Now you can remember the magnitude of force depends on 3 factors. What are the factors? One is the length of the conductor. Now here of course we can't change the length of the conductor. Then of course we'll need to have a larger magnet. If the length of the conductor is longer, you need to have a larger magnet. Otherwise what we can do is we can change the strength of the magnet. When the strength of the magnet increases also, the magnitude of force increases. And also depends on the magnitude of current flow. When the current flow increases, the strength of the force increases. The magnitude of force increases. So the magnitude of force depends on 3 factors. Length of conductor, strength of the magnet, and the magnitude of current. So when the force increases, the speed of movement of the conductor also increases. So the question is, how can you increase the speed of the movement of the conductor? So we can say by providing more current or increase the number of batteries. So one method, increase the number of batteries. So the current increases. So that is the easiest change that we can make. Otherwise, we can use a stronger magnet and also we can use a longer conductor. So that also is possible. Use a longer conductor. So 3 ways in which we can increase the speed of movement. So the easiest is to increase the number of batteries so that we don't need to change the magnet and the aluminium conductor BC. Otherwise, we will have to change the magnet as well as the conductor. So then also the speed of the movement will change. Is that clear, students? So then, part 8, the temperature of the aluminium conductor will increase when current flows continuously through it. That you all know. All the conductors have a resistance. Even though it's a good conductor, it has resistance. And there is a certain amount of current that is used against the resistance. So because of that, when there is current flowing through the conductor over a long period of time, there will be heat generated. So that is what is given here. Write a physical quantity of aluminium that will change with increase in temperature. What will increase? Now you all can remember, for a conductor, when the temperature increases, the random movement of the components, the constituent particles increases. So because of that, the resistance increases. So the physical quantity that will increase with increase in temperature is the resistance. So here, resistance increases. That means the conductivity will decrease. So here they have asked the question, write a physical quantity of aluminium that will change with increase in temperature. So resistance is a physical quantity. So if you say resistance increases, you all know the conductance or the conductivity of the conductor decreases. So you can write resistance or you can say conductance. Conductance decreases. So I'll write that also here. You have to write only one answer. Conductivity or conductance decreases. So you can write one of the factors. Both are related. When resistance increases, conductivity decreases. So you can write one of the answers. Is that clear, students? So those are the other two parts. Still the question is continuing. Part 9. How can you make the aluminium conductor to move in the same direction as you mentioned in part 3 above after changing the terminals of the battery? Now if we go back to part 3, you can remember initially it is out of the magnet. That was the first instance. Why? Initially the current flow was from A to B, B to C and C to D, and the magnetic field was from north to south. Now we have changed the terminals of the battery in this particular question. So here it is moving out of the magnet or away from the magnet. So how can you make the aluminium conductor to move in the same direction as you mentioned in part 3 above? So it has to be out of the magnet. Now here it should be away from the magnet. Out of or away from magnet. But you can remember after changing the terminals of the battery. When we change the terminals of the battery, the rod moved into the magnet. So I have told you all this. When we just make one change, direction of the force changes. But if you change both, the direction of the current flow as well as the direction of the magnetic field, then of course there will be no change. So how can you make the aluminium conductor to move in the same direction as you mentioned in part 3 above? Move in the same direction as you mentioned in part 3, that is away from the magnet after changing the terminals. So that is also important. after changing the terminals of the battery. So what can we do? Change the poles of the magnet. Change the poles of the magnet. Change the poles of the magnet. So here you can see initially, now the current flows this way, B to C. So current is flowing this way. Magnetic field is down. Thumb points outwards. So there the movement is away from the magnet. But then we have changed the batteries. So current is flowing there and the magnetic field down. So the movement is going to be inwards. But we want it to move outwards. So what can we do? We can change the magnetic field. Change the magnetic field. It is going to be north to south up. Current flows from C to B and the force is acting outwards. Then also you get the same observation. So here as it is, you can see current flow B to C. Magnetic field north to south, that is field. If we change both, if we change the current flow from C to B and also the magnetic field north to south, then still the direction of the force will remain the same. Here also it is out of the magnet, here also out of the magnet or away from the magnet. Is that clear, students? So here I have given the answer, that is the explanation. Then the 10th part. Illustrate the forces acting on the aluminium conductor when it is not moving. If it is not moving, then what is the force acting on the aluminium conductor? It is going to be the mass acting downwards. So because of that, mass into gravitational acceleration, weight. Weight is the force. So if we show the diagram, that is the so this is B, C rod. These are the brass rods. The weight will act downwards. And at these 2 points, there will be the reaction. Now here, you can see these 2 points. Where are the here and here? Where the rod is, the BC conductor is resting on the 2 brass rods. The brass rods will give a reaction. So the weight of the BC rod, that is the aluminium conductor, will be down and the reaction will be upwards. So that is how the equilibrium will exist. Weight is equal to the addition of the sum of the reactions. So there is no resultant force. The rod will be at rest. So here reaction will be equal to weight. Is that okay, students? You all can remember that. So this is illustrate the forces acting on the aluminium conductor when it is not moving. Since they have said illustrate, I have drawn a different diagram and shown it here. But if they should tell you all to mark it on the diagram, you have to do it there. Then the 11th part. Write a problem that will arise if an iron rod is used instead of the aluminium conductor. Now we all know aluminium is not a magnetic material. So because of that, when current flows through the aluminium rod, there is no magnetic field generated. Magnetic field is not generated. But if you have an iron rod, iron is a magnetic material. So when current flows through the magnetic material, that is iron, then there will be a magnetic field generated around that also. Magnetic effect of current. So because of that, the iron rod can either get attracted to the U magnet or will be pushed away, repelled by the magnet, or it will get attracted towards one of the poles. So there the observation can be disturbed. There will be a disturbance in the movement of the BC rod. So that would be the problem. So here, write a problem that will arise if an iron rod is used instead of the aluminium conductor. So here you can say that there will be a magnetic field acting around the iron rod when current flows through it. This will interrupt the movement of the conductor BC. So if you write that, that is more than enough. So there will be two magnetic fields acting. Magnetic field from the magnet, U magnet, and the magnetic field that is generated. So there can be a disturbance. Is that clear, students? So that is why we use an aluminium rod. So that will not get magnetized. So there will be a magnetic field acting around the iron rod when current flows through it. This will interrupt the movement of the conductor BC. Is that okay? So with that, I'll move on to the next slide. Extra question 7. Write the 3 factors that affect the magnitude of the force resulting from a current flowing through a conductor placed in a magnetic field. We have already discussed this. You can remember one factor, length of the conductor, or if it is a coil, that is again the number of turns in the coil, strength of the magnet, and the magnitude of current. The 3 factors. So here when we have the length of the conductor, strength of the magnet, magnitude of the current, and all these are directly proportional to the force. So when the length increases, force increases. When the strength of the magnet increases, the force increases. And when you increase the current flow, then also the force increases. All of them are directly proportional to the magnitude of force. Then, the next one, Fleming's left-hand rule is illustrated in the diagram given below. Write what is indicated by the 3 fingers. So here you can see this is the left-hand rule. So if you hold it this way, you can see red color arrow is the thumb. Thumb indicates the direction of the force. So this is the force. Then you can remember blue color arrow is the index finger. That indicates the direction of the magnetic field. And the green color arrow, that is the middle finger, that indicates the direction of the current flow. So the quantities are force, magnetic field, and current flow. So like this. This is current flow, middle finger, index finger magnetic field, and the thumb force. So that is what we need to write here. With that, students, I'll move on to the next question. Extra question 8. The action of a force on a current carrying conductor placed in a magnetic field is a very useful phenomenon in our daily lives. So you're familiar with that. The questions that we discussed before, they are based on that. When you have a conductor placed in a magnetic field, when current flows through it, there is a force acting on it. So the question is, write 5 instruments that use the above phenomenon. You're familiar with the instruments also. The direct current motor functions based on this. Then the loudspeaker, that also functions based on this. Then there are the devices, the galvanometer, the analog voltmeter and the analog ammeter. They also function based on this principle. So that is what we need to write here. 5 instruments. DC motor, the loudspeaker, galvanometer, ammeter, and voltmeter. These have to be the analog ones, not the digital ones. The analog ones are based on this principle. So DC motor, loudspeaker, galvanometer, ammeter and the voltmeter. So with that, students, I'll move on to the next question. Extra question 9. A direct current motor is shown in the diagram. So here you can see this is a direct current motor. So you can see these two parts labeled as N and S. So you know the north pole and the south pole. So that is the permanent magnet of the direct current motor. Then here you can see A, B, C, D is the wire loop. That represents the armature of the direct current motor. So this armature actually includes the wire loop. Then you can see the 2 split rings, the pink color and the green color rings labeled as X and Y. They are connected with the wire loop. So A is connected to X and D is connected to Y. Then at the same time you can see here P and Q, they are the brushes. You can remember carbon brushes. At this instance, ring X is in contact with P and the half ring Y is in contact with Q. And the external circuit, here you can see the power supply. This is the positive terminal, negative terminal. So current will flow from the batteries to P, then to X, then to A, B, C, D direction, back to Y and then Q. So that is how the current will flow. Then the magnetic field will be from north to south. So you all know there will be a force acting on AB part of the loop and CD part of the loop. So that will give rise to the rotation of the wire loop. So that is how the direct current motor functions. And you all know these split rings are there so that the current through the loop will be altered. That is, the direction of the current flowing through the loop will be altered during the rotation. Initially, it will flow from A, B, C, D direction after half a turn. Half a turn is 180 degrees turn. You know that DC will be on this side. So then current will flow in the direction DC, BA. Like that, the direction of the current flow through the loop will be altered by using the split rings. So you know the parts of the direct current motor. Now we will answer the questions. So here, first one, in what direction does the current flow in the wire loop? So you all know, as it is, since this is the positive terminal, current flows in the direction A, B, C, D. A, B, C, D. That you can remember. Then, second one, in what direction does the force act on the wire loop? AB. So AB is this part. Now what is the rule? What is the rule we need to apply here? Fleming's left hand rule. So in the Fleming's left hand rule, you all know middle finger is the direction of the current flow, index finger is the direction of the magnetic field, and thumb will point to the direction of the force. So here, north to south, magnetic field is this way. So index finger will be this way. The current flow is from A to B. So I have to turn my hand this way so that current is inwards, A to B. So the direction of the force is downwards. So loop AB, the force is acting downwards. So the loop AB will move down. In what direction does the force act on the wire loop AB? Downwards. Downwards. So here they have asked in what direction. So the force is downwards. Then, what rule did you use to predict the direction of the force? Fleming's left hand rule. Fleming's left hand rule. So those are the first few parts. I'll continue with the question. Part 4. Will there be a force acting on the loop BC when a current flows through the wire loop? Briefly explain your answer. The BC. Now here you can see BC is this way. Now current will flow in this direction, and you can see the blue color lines indicate the magnetic field. So blue color lines indicate the magnetic field, north to south. Even if they don't give you the poles N and S, north and south, by looking at these lines, you all know the magnetic field is in this direction. So this has to be the north pole and that has to be the south pole. Now that is this direction. When current flows from B to C or C to B, there again that direction is parallel to the magnetic field. Now you all know for the force to act, the magnetic field, direction of the current flow and the force are perpendicular to each other. Here the conductor and the magnetic field are parallel. Because of that, there is no force acting on BC. Is that clear, students? So that is something we need to write. Will there be a force acting on the loop BC? No. When a current flows through the wire loop, briefly explain your answer. Conduct loop BC is parallel to the direction of magnetic field. So therefore, there will be no force acting on it. So to answer the question, will there be a force acting on the loop BC when a current flows through the wire loop? No. Briefly explain your answer. Loop BC is parallel to the direction of magnetic field. Therefore, there will be no force acting on it. So that is the explanation. Even if you just say BC is parallel to the direction of the magnetic field, that is also enough. You give the explanation. Right. So then the next part, part 5, in what direction will the wire loop rotate due to the force generated when a current flows through it? In what direction will the wire loop rotate? Now we already saw that here AB, the wire loop, the force is downwards. The same way if you apply the Fleming's left hand rule to CD, what happens there? Current flows in the direction CD. Magnetic field lines are this way, north to south. So the force is up. So CD will move up and BC will move down. So the rotation will be this way, this way. What is that direction? Clockwise direction. So here you can see in what direction will the wire loop rotate due to the force generated when a current flows through it? Clockwise direction. I'm sure you all can understand that, students. Always for a direct current motor, to consider the rotation, we need to find the direction of the force. For that, we use the Fleming's left-hand rule. So there, the wire loop rotates in the clockwise direction. So with that, I'll move on to the next question. Part 6. What is the function of X and Y? Now here, X and Y, I told you all, they are split rings. X and Y, they are split rings, or what you call as commutator rings. And what is the function? They alternate the current, direction of current flowing through the wire loop ABCD. So initially it will flow in the direction ABCD. After half a turn, current will flow in the direction DCBA. So that is what you need to write here. The split rings X and Y alternate the direction of current flow through the wire loop. That is ABCD and DCBA directions. So this is to give a better understanding. The split rings X and Y alternate the direction of current flow through the wire loop. So ABCD and DCBA directions. Then, what is the energy conversion taking place in a direct current motor? What is the energy conversion? We supply current, so that is current energy, electric energy, and then the motor rotates. So when something rotates, moves, it's kinetic energy. That means it is mechanical energy. So here, electric energy is converted to mechanical energy. Mechanical energy. Is that okay, student? So that is the energy conversion. Electric energy to mechanical energy. With that, I'll move on to the next slide. Part 8. What will happen to the rotation of the wire loop if the terminals of the battery are interchanged? So, if the terminals of the battery are interchanged, what will happen there? Then, of course, you will have the positive terminal here, negative terminal there. Then the current flow will be in the direction initially DCBA. So, what happens there? The DC part of the loop, field is in the direction north-south, current is flowing inwards, so the loop, the force will act downwards. So, DC force is acting downwards, DC. At the same time, AB, in what direction does the force act? So, AB current will flow this way. So, their current flows this way, field that way, the force will act upwards. So, force will act upwards. Then, of course, the rotation will be like that. It is going to be anti-clockwise rotation. anti-clockwise. So the force down, force up. Why? Because the current flows this way, current I, and current flows this way here. So always we use the Fleming's left-hand rule. Current is flowing in DC direction. Magnetic field is still the same, force downwards. Here current is flowing outwards. Magnetic field again north to south. Force is acting upwards. So the rotation is like that. It is going to be anti-clockwise rotation. So anti-clockwise rotation. Anti-clockwise rotation. Then part 9. Write 2 changes that could be made to rotate the wire loop faster. Now you all know there are different factors, actually 3 factors that affect the magnitude of the force. The length of the conductor or the number of turns in the wire loop, so length of the conductor. Then you have the strength of the magnet and also the magnitude of current. So write 2 changes that could be made to rotate the wire loop faster. All the factors are directly proportional to the magnitude of force. When force increases, the speed of rotation will increase. So we can use a stronger magnet or we can use more batteries to increase the current flow. Here of course we can't change the length of the conductor because it's the same loop. So we can say increase the strength of the magnet or use a stronger magnet. Use a stronger magnet. And also use more batteries. You can say use more batteries or you can say increase the voltage. Now here you can see there are 2 batteries, 1.5 volt battery, so 3 volts. Instead if you use a 9 volt battery, then also the current will increase. So either you can use more batteries or you can increase the voltage of the batteries. And also you can use a stronger magnet in order to increase the force and make the loop to rotate faster. Is that clear, students? Then 10th one, what part of the motor is illustrated using the wire loop? What part of the motor? It is the armature. Armature. Now you all know, students, in the real motor, in order to rotate the load that is connected to the motor, usually the armature is made by winding a wire coil around, it's usually a copper wire coil, winding a copper wire coil around a soft iron core, so that it provides the strength to rotate the load as well. So the armature is usually the soft iron core around which the copper wire coil is wound. So that is represented by the ABCD loop. Is that clear, student? So then I'll move on to the next question. Extra question 10. So the first question, first part, what is electromagnetic induction? What is electromagnetic induction? Now all this time we were discussing the magnetic effect of current and how the force acts on a conductor placed in a magnetic field when there is current flowing through it. Electromagnetic induction is the opposite of that. Now you can remember there is a magnetic field, we have a conductor placed in it, but the conductor can move when the magnetic field is constant, or when the conductor is at rest, the magnetic field can change. You can rotate the magnet. Then of course there will be an induced electromotive force that gives rise to the induced current. And that concept is what we call as electromagnetic induction. So what is electromagnetic induction? An electromotive force is induced when a conductor moves in a constant magnetic field, or a magnet moves when the conductor is at rest. This is known as electromagnetic induction. So you need to have a conductor. There should be a magnetic field. The conductor should move when the magnetic field is stationary. When the magnetic field is constant, the conductor should move. Or when the conductor is at rest, the magnet should move. So then there will be an electromotive force induced, and that is known as electromagnetic induction. So here, who introduced electromagnetic induction to the world? Who introduced electromagnetic induction? Michael Faraday. So here, Michael Faraday. He is the one who first introduced electromagnetic induction to the world, Michael Faraday. So here, students, we have defined what electromagnetic induction is. That is, an electromotive force is induced. If it is better if you write as an electromotive force is induced across the conductor. Across the conductor. When a conductor moves in a constant magnetic field, or a magnet moves when the conductor is at rest. And this is known as electromagnetic induction. And this was introduced to the world by Michael Faraday. So you all can remember that, student. So with this, I am going to end this chapter, and in the next chapter also, I will discuss some more extra questions with you all.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.